Good morning, everyone. We've done some problems with kinetic friction already, and if we haven't yet, we definitely will encounter problems with static friction. And so the question remains, how many different types of friction are there? Are there more than just the kinetic and the static out there? And the answer is yes. I'd like to introduce you to the concept of rolling friction, specifically the rolling friction of a bicycle tire in this problem. So we have two bicycle tires that are set rolling with the same initial speed on a long straight road. And we are measuring the distance that each tire is traveling before its speed is reduced by half. Okay, so here's our initial speed, and then the final speed will be this value cut in half. Just a heads up. One tire, tire number one here, is inflated to 40 psi, and the distance that it travels is 18.1 meters. And then for tire number two, we are inflating that to 105 psi, and it travels a significantly longer distance, 92.9 meters. And so what do we have to do here? We need to solve for the coefficient of rolling friction for each tire. And to help with that, we get to assume that the net horizontal force is due to rolling friction only. So there's nothing else going on here. What does that mean? What does that look like? Let's draw a free body diagram of the tire. We have a couple forces that we have to account for. The first one being the tire's weight, which will pull straight down. Since the tire is not flying into the air or sinking down into the ground or something, there's going to be a normal force, and it's going to be equal and opposite to the weight, and one left. We were told that the horizontal movement is due to the rolling friction only. So let's go ahead and plug the rolling friction vector in, which will be pointing in the negative x direction to resist the tire's motion as it's rolling in the plus x direction. And here's a helpful reminder. Since the tire is slowing down, our acceleration is going to be pointing in that same direction as the rolling friction, right? So we'll kind of use this information along with the sum of forces to try to figure out what the coefficient of rolling friction would be for this vector. So if I kind of pull this all over to the left side of the screen and compile it together, let's start at the top of the page with F equals ma. And we're going to move into the sum of forces into the x direction first. And normally we have positive F equals positive ma, but check this out. The rolling friction and the acceleration are both pointing in the left direction. So it's negative F equals negative ma. But, since we have a negative on both sides, we can just get rid of it. Doesn't really matter. We do need to be very careful about the way that things are pointing, though. So it is important to kind of note this as a first step, even though we're getting rid of these negative signs here. So speaking of steps, what is the next step? Well, there won't be any negatives, and we'll be converting the expression for the rolling friction to mu sub r times the normal force, right? And here is our sum of forces in the y direction, where we will be able to kind of get an expression for what the normal force is. And that's really easy. We can just move the weight over to the other side, and we can exchange it for mg. And, well, that's cool. We can bring mg in over on the left-hand side here for n. So now we have mu sub r mg equals ma. Since we have a mass on both sides, we can cancel that out. And what we ultimately want to solve for is the coefficient of rolling friction. So let's divide both sides by g. And while this is helpful, we don't know what this is. We have no idea what the acceleration is. We weren't given that in the problem description. So what are we supposed to do? I would recommend uh, using kinematics to solve for this value. And in fact, we'll do that in the next slide here, using this equation. Now, normally, you might see this expression with a plus sign in it, and that is assuming that the acceleration is positive. Ours is not. It's negative. Okay, so I've switched that positive for a negative here, just a heads up. And what do we want to do? We want to solve for the acceleration happening in the x direction. So I am going to subtract the initial velocity squared on both sides, which will give me this. And then I will divide both sides by 2 times the distance that the tire travels before it reduces its speed by half. And here's a trick that I'm going to do when I multiply both sides by -1. I'm going to really just switch these two in the numerator here, where the acceleration will become positive on the right-hand side, and then we'll just have the initial velocity squared first, followed by the final. And hey, now we have an expression for the acceleration, and we can plug that back in to our equation down here. And we'll have to do a lot of algebra, so I'm going to do that from left to right to kind of avoid doing this on another slide. So forgive me if it's a lot of work here, but I'll talk my way through it. What I'm going to do is plug in this expression up here into the numerator for the acceleration, just like this. And what should we immediately do next? Well, there is a denominator in the numerator, which is kind of annoying to look at. So let's bring that downstairs into the denominator where it belongs, like this. One thing that we should remember about the final velocity from the problem description is that it was the initial velocity divided by 2. So since we don't know what the final velocity is, we can just replace initial velocity divided by 2 and square it. So then it's in terms of everything that we do know. And what does it look like when we do that? Well, we'll still have this term out front, but we'll have v initial squared, but divided by 4. Why? Because of this 2 in the denominator that gets squared. And what I would recommend doing is factoring out the initial velocity squared from everything in the numerator here. So it should look like this. So check this out. We have a pure number now in the parentheses, which, I mean, that's really easy. You can convert 1 to the following if you're not comfortable with doing this kind of expression here. 1 is equal to 4 over 4, and 4 minus 1 is just 3. So we have the initial velocity squared times 3 over 4 in the numerator. However, we have that same kind of issue going on where we had over here, where there's a denominator in the numerator. That's kind of annoying. Let's bring it downstairs where it belongs, like I said. And that will mean we have 3/8 as a coefficient, a final coefficient, which I'm going to write in bold here, and I'll bring that out front. And then a bunch of variables in terms of things that we do know, right? We were given this. We know what G is, always, and we were given delta X for both tires. So now we can just plug in all of our numbers and we're done. So let's calculate the rolling friction for both tires. I'll plug in the coefficient of rolling friction for tire number 1, and we're using that expression that we just solved for. And what am I plugging in? Well, the initial velocity, squaring it. I know what G is, and the distance that the first tire went. And I get this on my calculator here. and when I approximate to the correct number of significant figures, I get that number. What about the second tire? Well, same process, same equation, but delta x is much bigger now. So that means we should expect what? We should expect our rolling friction number to be much smaller because we have the same numerator for a much larger denominator now. And that is exactly what you get. At least that's what I get on my calculator. And to 3 significant figures, it is indeed much smaller. And that is it. That is the coefficient of rolling friction for both tires. And we did it. Thanks for watching.